Look up at the night sky. What do you see? A vast, endless expanse of stars, galaxies, and mysteries stretching far beyond what our eyes can comprehend. But what lies beneath that shimmering veil? What invisible, unimaginable forces are at work, shaping the very fabric of reality itself? The universe isn't just a collection of celestial objects, it's a dynamic, ever-changing arena where colossal powers collide, twist, and rewrite the rules of existence. From the crushing grip of black holes to the enigmatic push of dark energy, these forces don't just influence the cosmos, they define it. Think about this for a moment. Every second, unseen energies are stretching space apart, hurling galaxies away from each other, while gravitational titans warp time itself. These aren't just abstract concepts, they're the hidden architects of everything we know. And today, we're about to uncover the 30 most powerful forces in the universe, each one more awe-inspiring than the last. Some will feel familiar, like the gravity that keeps your feet on the ground. Others will defy logic, bending the limits of what we thought possible. What if I told you there's a force so potent it can tear stars apart, or one so mysterious that it makes up nearly 70% of the universe, yet we've barely begun to understand it? This isn't science fiction, it's the reality we live in. These forces are the reason galaxies spin, stars ignite, and the cosmos evolves. They've sculpted the universe over billions of years, and they're still at work right now all around us. So buckle up, because we're about to embark on a journey through the most extreme, mind-bending powers that govern existence itself. By the end, you'll never look at the night sky the same way again. Gravity is the silent architect of the cosmos, the force that sculpts planets, binds galaxies, and bends the very fabric of space and time. Imagine tossing a ball into the air. It arcs back to Earth, pulled by an invisible hand. Now scale that up. Picture entire worlds locked in an endless dance around stars, or galaxies swirling in vast cosmic orbits. That's gravity's handiwork, but it's so much more than just what goes up must come down. Einstein revolutionized our understanding with his theory of relativity, revealing that gravity isn't just a force, it's the curvature of spacetime itself. Massive objects like stars and planets dent this fabric, like a bowling ball sinking into a trampoline. Smaller objects like asteroids or even light follow these curves, creating the orbits and paths we observe. Take black holes, for instance. These gravitational monsters warp spacetime so severely that not even light can escape their grip. Near their edges, time slows to a crawl, a phenomenon straight out of science fiction, yet proven by real-world observations. Then there's gravitational lensing, where the gravity of a massive galaxy cluster bends light from objects behind it, acting like a cosmic magnifying glass. This isn't just theoretical. Astronomers use it to peer deeper into the universe than telescopes alone could ever reach. But gravity's influence stretches even further. It's the glue holding galaxies together, preventing stars from drifting into the void. Without it, the Milky Way would fly apart, and solar systems like ours would never have formed. Every spiral arm, every planetary orbit, every tidal wave on Earth is a testament to gravity's quiet, relentless power. And yet, for all its dominance, it's the weakest of the fundamental forces, a paradox that still baffles physicists. How can something so fragile at the atomic scale wield such control over the cosmos? That's the enigma of gravity, a force we experience every day, yet one that continues to reveal its secrets in the grandest ways imaginable. While gravity may be the architect shaping the vast cosmos, electromagnetism is the artist painting the universe with light, binding atoms together and powering nearly every piece of technology in our daily lives. Picture this: every time you flip a light switch, scroll on your phone, or even feel the warmth of sunlight, you're experiencing the same force that makes stars shine and auroras dance across polar skies. Electromagnetism is the interplay of electricity and magnetism, a force so powerful that, at the atomic scale, it's over a trillion times stronger than gravity. That means the tiny magnetic pull keeping your fridge door shut outweighs the entire Earth's gravitational tug on it. How does this force work? At its core, electromagnetism governs how charged particles interact positively charged protons and negatively charged electrons spinning in a delicate cosmic ballet. When these charges move, they create magnetic fields, and when magnetic fields shift, they generate electric currents. This endless cycle is what powers everything from the lightning crackling in a thunderstorm to the precise signals firing in your brain. Take light, for example. It's just another face of electromagnetism, an electromagnetic wave traveling through space, carrying energy from distant stars to our eyes. Without this force, the universe would be utterly dark. Then there's chemistry itself. The reason atoms bond to form molecules, the building blocks of life, comes down to electromagnetic attraction. Oxygen clings to hydrogen to make water, carbon weaves into complex chains to create DNA, and metals conduct electricity, all because of this invisible force. But where electromagnetism truly dazzles is in human ingenuity. MRI machines use powerful magnetic fields to peer inside our bodies, revealing injuries and illnesses without a single incision. Auroras, those shimmering curtains of color in polar skies, are nature's own light show charged particles from the sun colliding with Earth's magnetic field, releasing bursts of radiant energy. Even something as simple as a compass needle pointing north is electromagnetic magic, the planet itself acting like a giant magnet, guiding explorers for centuries. Yet for all its might, electromagnetism has limits. Unlike gravity, which stretches infinitely across space, its influence weakens rapidly over short distances. That's why you don't feel a spark when walking past a power line, even though electrons are racing through it. This balance, strong enough to shape matter, yet contained enough to allow stable structures, makes electromagnetism the perfect force for building complexity in the universe. From the smallest atom to the brightest quasar, it's the silent pulse behind nearly every phenomenon we see and touch. And as we harness its power in ever more advanced ways, we're not just observing nature's rules, we're learning to rewrite them. While electromagnetism paints the universe with light and color, there's a force working at scales so small, our eyes could never perceive it, yet without it, matter as we know it wouldn't exist. Meet the strong nuclear force, nature's ultimate glue. Picture the nucleus of an atom where protons pack together so tightly, their positive charges should blast them apart with unimaginable force. But they don't. Why? Because the strong nuclear force overpowers even electromagnetism, holding nuclei together with a grip so fierce it defies intuition. This force operates in two extraordinary ways. First, it binds quarks, the fundamental building blocks of protons and neutrons, locking them together so tightly that trying to pull them apart only creates new particles. Imagine stretching a rubber band until it snaps, only for the broken ends to instantly form new rubber bands. That's quark confinement in action. Second, it extends its reach just beyond protons and neutrons, creating a nuclear cement that prevents atomic nuclei from flying apart. Without it, every atom in your body would disintegrate in an instant. The numbers behind this force are staggering. At its peak, the strong nuclear force is about 100 times stronger than electromagnetism and a staggering 10 to the power of 38 times stronger than gravity. That's a 1 followed by 38 zeros. To put that in perspective, if gravity were a whisper, the strong nuclear force would be a supernova. We harness this power in places like the Large Hadron Collider, where smashing protons at nearly light speed lets us glimpse the force's raw energy. These collisions recreate conditions from the early universe when quarks roamed freely in a searing plasma. Even the sun relies on the strong nuclear force. Its fusion reactions occur because this force lets hydrogen nuclei overcome their electromagnetic repulsion and merge, releasing the sunlight that fuels life on Earth. Yet for all its might, the strong nuclear force has a curiously short leash. Its influence stretches only about the width of an atomic nucleus. Step beyond that, and it vanishes entirely, which is why we don't feel its pull in everyday life. This precision is what makes it so perfect, strong enough to forge the building blocks of matter, yet precise enough to let atoms and chemistry exist. Without it, there'd be no stars, no planets, no us. It's the invisible hand that built the visible universe, one nucleus at a time. While the strong nuclear force binds atoms together with unshakable might, its mysterious counterpart, the weak nuclear force plays by entirely different rules. This is the force behind some of the universe's most transformative events, the silent decay of atoms, the fiery heart of stars, and even the creation of gold in the violent deaths of massive suns. Unlike gravity or electromagnetism, its influence is subtle, operating almost like a cosmic alchemist, transforming one element into another in processes so fundamental, they quite literally shape the matter around us. Radioactive decay is the weak force's signature move. Picture an unstable atomic nucleus, its protons and neutrons jostling like restless passengers on a crowded train. Suddenly, a neutron can't take the tension anymore. It transforms into a proton, ejecting an electron and an almost ghostly particle called a neutrino. This is beta decay, and it's happening right now in rocks beneath your feet, in the air you breathe, even inside your own body. Potassium-40 in bananas. That's the weak force at work. Carbon-14 used to date ancient artifacts, same story. These tiny transformations power everything from nuclear reactors to the smoke detectors in your home. But the weak force's reach extends far beyond Earth. Inside stars like our Sun, it's the hidden engine of fusion. When hydrogen nuclei collide, the weak force lets protons convert into neutrons, forging helium and releasing the energy that bathes our planet in light. Without this process, stars would flicker out, leaving the universe cold and dark. Then there's its grandest act, the creation of heavy elements. When a massive star goes supernova, the weak force orchestrates a chaotic dance of particles, allowing neutrons to bombard atomic nuclei. This builds elements like uranium, platinum, and gold, stuff that eventually ends up in everything from jewelry to nuclear fuel. Even the iron in your blood owes its existence to this force's delicate balancing act. Here's what makes the weak force truly bizarre. It's the only force that changes the identity of particles. Gravity bends paths, electromagnetism pushes and pulls, but the weak force rewrites the rules. It's also shockingly short-ranged. Its influence vanishes beyond a distance 100 times smaller than an atomic nucleus. Yet despite its elusive nature, we've harnessed its power in medicine, energy, and even probing the secrets of the universe itself. Neutrino observatories buried deep underground catch particles the weak force creates, offering us whispers from the sun's core and distant supernova. So while it may not hold galaxies together or light up the sky, the weak nuclear force is the universe's ultimate transformer, turning energy into matter, shaping the elements of life, and quietly powering the cosmos one radioactive heartbeat at a time. Just when we thought we had the universe figured out, along comes dark energy, the most baffling, dominant force in existence. Imagine waking up one day to discover that everything around you is stretching apart faster and faster with no breaks in sight. That's precisely what's happening to our cosmos right now, and dark energy is the invisible hand behind it all. Astronomers first stumbled onto this mystery in the late 1990s when teams studying distant supernova made a jaw-dropping realization. The universe wasn't just expanding, it was accelerating. This was like throwing a ball in the air only to watch it shoot upward faster and faster, defying gravity's pull. The culprit, a mysterious repulsive force dubbed dark energy, making up roughly 68% of the universe's total energy. Think about that for a second. Nearly 7/10 of everything that exists is something we can't see, touch, or even fully comprehend. Hubble Space Telescope images reveal the eerie fingerprints of dark energy in the way galaxies flee from one another. The deeper we look into space, the faster these galaxies appear to recede, as if space itself is being stretched from within. One leading theory suggests dark energy is woven into the fabric of the vacuum, a constant energy density known as the cosmological constant, an idea Einstein once proposed and later dismissed as his biggest blunder. Turns out he might have been onto something after all, but here's where it gets even stranger. If dark energy continues unchecked, it could lead to the Big Rip, a scenario where the force grows so powerful that it tears apart galaxies, then stars, then even atoms themselves. Alternatively, some models suggest dark energy might fluctuate or fade, potentially leading to a big crunch where the universe collapses back in on itself. Or worse, a silent, cold heat death, where expansion leaves the cosmos a vast, empty wasteland. Yet despite its overwhelming influence, dark energy remains a ghost in the equations. Is it a property of space itself, a new kind of field, or evidence of undiscovered physics beyond Einstein's theories? Projects like the Dark Energy Survey and the upcoming Nancy Grace Roman Space Telescope aim to crack this enigma, mapping galaxies in unprecedented detail to trace dark energy's grip on cosmic history. What's certain is this: dark energy holds the keys to the universe's ultimate fate. It's rewriting the story of everything we know, one accelerating galaxy at a time. And as we peer deeper into the void, we're not just searching for answers, we're racing against the expansion of space itself, trying to decode the universe's final chapter before it slips forever beyond our reach. Dark matter is the universe's greatest vanishing act, an invisible scaffold shaping everything we see, yet completely undetectable by ordinary means. Picture a cosmic puppeteer pulling strings we can't see, but whose effects are written across the night sky. Unlike dark energy, which pushes the universe apart, dark matter pulls it together with gravity, weaving a hidden architecture that holds galaxies in place. Without it, the Milky Way would spin itself apart like a carousel with no center pole. Take galaxy rotation, for instance. In the 1930s, astronomer Fritz Zwicky noticed something bizarre. Galaxies in clusters were moving so fast, their visible mass shouldn't have been enough to keep them bound together. Decades later, Vera Rubin found the same mystery on smaller scales. Stars at the edges of spiral galaxies orbit just as fast as those near the center, defying the laws of gravity as we knew them. The only explanation, an invisible halo of dark matter, its gravitational grip countering what should be a deadly cosmic slingshot. Then there's the cosmic web, a vast, tangled network of dark matter filaments stretching across the universe like invisible highways. Supercomputer simulations reveal how these threads guide ordinary matter, funneling gas into the intersections where galaxies ignite. Without this hidden framework, the universe would be a scattered haze of gas, never condensing into the glittering cities of stars we see today. Perhaps the most jaw-dropping evidence comes from collisions like the Bullet Cluster. When two galaxy clusters smash together, their visible gas are hot and slow, piled up in the center like cosmic traffic jam. But their dark matter, it sailed right through, revealed only by how its gravity bent the light of more distant galaxies, leaving ghostly imprints in space-time. This wasn't just proof of dark matter's existence, it was a cosmic autopsy showing how it behaves unlike anything made of atoms. Yet for all its influence, dark matter remains frustratingly elusive. It doesn't emit, absorb, or reflect light, hence the name. It could be made of undiscovered particles streaming through your body right now without a trace. Or perhaps it's evidence our understanding of gravity is incomplete. Projects like the Large Underground Xenon experiment hunt for dark matter particles in abandoned gold mines, while the Euclid Space Telescope maps its distribution across billions of light years. One thing's certain, dark matter is the universe's silent partner, a shadowy collaborator in the story of stars, planets, and life itself. Without it, galaxies wouldn't form, stars wouldn't ignite, and we wouldn't be here to ponder the mystery. It's a reminder that what we see is just the tip of the cosmic iceberg and that the greatest forces in existence might be the ones we can't even see. Black holes aren't just cosmic vacuum cleaners, they're the ultimate spacetime maestros, twisting the universe into impossible shapes. Imagine a place where gravity wins every battle, where even light surrenders to the abyss. At the heart of every black hole lies the singularity, a point of infinite density where the laws of physics as we know them simply break. But it's the boundary around this oblivion, the event horizon, that marks the point of no return. Cross it and there's no coming back, no signal, no cry for help. Time and space switch roles, turning forward toward the center, like some nightmarish cosmic treadmill. Yet black holes aren't just destroyers, they're also creators. Take the dazzling accretion disk, a swirling vortex of superheated gas and dust spiraling inward at nearly light speed. Friction heats this material to millions of degrees, making it glow brighter than entire galaxies. Quasars, the most luminous objects in the universe, are powered by supermassive black holes feasting on these disks, their light visible across billions of light years. Even our own Milky Way harbors a quiet giant, Sagittarius A, occasionally flaring to life when a stray star or gas cloud veers too close. Then there's the music of black holes, gravitational waves. When two of these titans collide, they send ripples through spacetime itself, distortions so subtle that it took lasers and mirrors spanning continents to detect them. The first confirmed merger, observed in 2015, released more energy in a fraction of a second than all the stars in the observable universe combined. These waves aren't just cosmic curiosities, they're a new language for studying the universe, revealing black holes we'd never see with light alone. But perhaps the strangest twist is what happens to matter inside a black hole. According to quantum mechanics, information can't be destroyed, yet general relativity suggests it's obliterated at the singularity. This black hole information paradox has sparked decades of debate, with theories like Hawking radiation proposing that black holes might slowly evaporate, leaking particles back into the universe over unimaginable eons. From bending light into surreal rings to hurling stars across galaxies like cosmic slingshots, black holes redefine what's possible. They're not just objects, they're laboratories for the most extreme physics, testing our understanding of reality itself. And as we peer deeper into their shadows, we're not just uncovering the secrets of the universe, we're staring into the mirror of its most profound mysteries. Neutron stars are the universe's ultimate pressure cookers, cosmic relics so dense they defy common sense. Picture crushing the entire mass of our sun into a sphere no wider than Manhattan. The result, a teaspoon of neutron star material, would weigh over 1 billion tons on Earth, more than Mount Everest crammed into a sugar cube. These stellar corpses are born from the explosive deaths of massive stars, where gravity wins a brutal tug of war, compressing protons and electrons into neutrons with such force that atoms themselves cease to exist. What remains is a seething ball of nuclear matter, spinning faster than a kitchen blender and crackling with magnetic fields strong enough to strip the data from every credit card on Earth, from halfway across the Milky Way. Take their magnetic fields, for example. Ordinary neutron stars boast fields 1 trillion times stronger than Earth's, but their mutated cousins magnetars take this to comic book extremes. Their magnetic fury is so intense, it can fracture the star's rigid crust, triggering starquakes that release gamma-ray flares visible across intergalactic distances. One such eruption in 2004 briefly ionized Earth's upper atmosphere from 50,000 light-years away, as if the cosmos had flicked us with a celestial rubber band. Then there's their dizzying rotation. Fresh neutron stars can spin hundreds of times per second, their surfaces whipping around at nearly a quarter the speed of light. As they age, they emit beams of radiation from their magnetic poles, sweeping across space like interstellar lighthouses. When these beams cross Earth's path, we detect them as pulsars, the universe's most precise timekeepers. Astronomers have used pulsars to test Einstein's theories, map the Milky Way's structure, and even carry messages for potential extraterrestrial civilizations on the Voyager golden records. Yet neutron stars aren't just cosmic oddities, they're alchemists of the extreme. When two collide, the violence forges heavy elements like gold, platinum, and uranium in a radioactive firework display. The gravitational waves from such mergers ripple through spacetime, while the aftermath glows with a kilonova, a beacon signaling the birth of precious metals. That wedding ring on your finger, its atoms were likely forged in a neutron star collision billions of years before our solar system existed. From bending light around their edges like a funhouse mirror to serving as natural laboratories for quantum physics, neutron stars push matter to its breaking point. They're reminders that the universe's most astonishing creations often lurk in the ashes of catastrophe, and that inside every tiny, impossibly dense sphere lies the heart of a fallen giant. Supernovae are the universe's grandest spectacles, cosmic fireworks that outshine entire galaxies while forging the very elements that make life possible. Imagine a star millions of times brighter than our sun, suddenly detonating with the force of 1 billion nuclear bombs. In mere seconds, it releases more energy than our sun will over its entire 10 billion-year lifespan. But these explosions aren't just destructive, they're transformative, scattering stardust across the cosmos like celestial farmers sowing seeds for future worlds. Take the famous Crab Nebula, the aftermath of supernova SN 1054, a blast so bright it was visible in broad daylight for 23 days and recorded by astronomers across China and the Middle East. Today, its remnants still glow, a tangled web of gas and dust spinning off a pulsar at its heart. But what makes supernova truly astonishing is what happens inside the inferno. As the collapsing star's core reaches unimaginable temperatures and pressures, atoms are smashed together in a frenzied nuclear dance, forging elements like iron, gold, and uranium, stuff that eventually ends up in everything from smartphone circuits to the hemoglobin in your blood. There are two primary ways a star goes supernova. Massive stars, at least 8 times heavier than our sun, collapse under their own gravity when they exhaust their nuclear fuel, triggering a shock wave that rips them apart. White dwarfs, the dense remnants of smaller stars, can reignite in a thermonuclear runaway if they steal too much mass from a companion, detonating like a cosmic grenade. Both scenarios unleash torrents of neutrons which bombard lighter elements to create heavier ones, a process called rapid neutron capture, or the R process. It's how gold, platinum, and other precious metals are born. The fallout from these explosions is breathtaking. Supernova remnants like Cassiopeia expand for thousands of years, their shockwaves compressing nearby gas to birth new stars. The iron in your blood, the calcium in your bones, even the iodine in your thyroid, all were forged in these stellar furnaces and hurled into space by their violent deaths. Without supernova, the universe would lack the chemistry for planets, oceans, or life itself. But their influence doesn't stop there. Some supernova act as cosmic measuring sticks. Type Ia explosions, which always peak at the same brightness, allow astronomers to calculate vast distances across the universe, a tool that famously revealed dark energy's existence. Others, like the recent supernova 2023 IXF in the Pinwheel Galaxy, offer rare glimpses into the death throes of stars in real time, their light curves painting a portrait of elemental creation in action. From sculpting galaxies to seeding the ingredients of life, supernovae are the universe's ultimate recyclers. They remind us that destruction and creation are two sides of the same cosmic coin, and that every atom in our bodies was once part of something far greater, a star that lived, died, and scattered its ashes across the void. Gamma-ray bursts are the universe's ultimate death rays, cosmic tantrums so violent, they outshine everything else in the sky for fleeting moments. In the span of a few seconds, a single burst can release more energy than our sun will emit over its entire 10 billion-year lifetime. These aren't just bright flashes, they're apocalyptic events capable of sterilizing entire planets thousands of light years away, and the scariest part, we're still unraveling what triggers them. Picture this: in the late 1960s, military satellites designed to detect nuclear explosions began picking up mysterious gamma-ray signals from deep space. At first, scientists suspected Soviet bomb tests until they realized the bursts were coming from all directions, far beyond our galaxy. Today, we know these signals are the last screams of dying stars or the collision of ultra-dense stellar remnants. But their power is almost incomprehensible. A typical gamma-ray burst pumps out as much energy in 10 seconds as a supernova does in months. There are two main types, each more terrifying than the last. Long-duration bursts, lasting from 2 seconds to several minutes, are thought to be the death throes of massive, rapidly spinning stars collapsing into black holes. As the star's core implodes, twin jets of radiation blast outward at nearly the speed of light, piercing through the star's outer layers like a blowtorch through paper. If one of these jets points at Earth, we see it as a gamma-ray burst bright enough to outshine 1,000,000 trillion suns. Short-duration bursts lasting less than 2 seconds are even more exotic. These are likely caused by neutron stars colliding, a cataclysm so violent it warps spacetime and forges heavy elements like gold in its wake. The kilonova explosion that follows glows with radioactive light, but the initial gamma-ray flash is what punches through the cosmos like a lightning bolt. But what makes these bursts truly lethal isn't just their brightness, it's their aftereffects. A nearby gamma-ray burst could strip Earth's ozone layer, bathing the surface in deadly ultraviolet radiation. Scientists suspect one may have triggered the Ordovician mass extinction 450 million years ago, wiping out nearly 85% of marine life. Even today, astronomers track these events with urgency. The Swift and Fermi satellites scan the skies daily, capturing light curves that reveal the burst structure, a rapid rise, a brilliant peak, then a slow fade as the jet's energy dissipates. Yet for all their destructive power, gamma-ray bursts are also cosmic lighthouses. Their light travels billions of years, letting us probe the early universe's chemistry. Some bursts even help measure the rate of cosmic expansion, serving as mile markers in the vast dark. They remind us that the universe isn't just beautiful, it's volatile, unpredictable, and capable of unleashing forces beyond our wildest imagination. And as we watch these fleeting flashes, we're not just witnessing stellar deaths, we're glimpsing the raw power that shaped the cosmos itself. Cosmic inflation is the universe's most extreme growth spurt, a fraction of a second when space itself expanded faster than the speed of light, smoothing and stretching the cosmos into the vast, flat expanse we see today. Picture blowing up a balloon with tiny wrinkles drawn on its surface. As the balloon inflates, those wrinkles stretch out, becoming smoother and fainter. Now imagine that balloon is the entire universe, and the inflation happens in less time than it takes light to cross a single atom. That's the sheer scale of this phenomenon, an event so brief yet so transformative it set the stage for everything that followed. The evidence for inflation is etched into the oldest light we can see, the cosmic microwave background, or CMB. This afterglow of the Big Bang, captured in stunning detail by satellites like Planck and WMAP, reveals a universe almost perfectly uniform in temperature, but with whisper-faint variations. These tiny fluctuations, no stronger than 1 part in 100,000, are the cosmic seeds that gravity would later sculpt into galaxies and galaxy clusters. Without inflation's rapid smoothing, the universe would be a chaotic patchwork of hot and cold regions, far too uneven for structures like our Milky Way to form. But how could space expand faster than light? Here's the twist. While nothing can move through space faster than light, space itself has no such speed limit. Think of ants crawling on a rubber sheet. If the sheet stretches faster than the ants can walk, they'll never reach each other even though they're not breaking any ant speed limits. Inflation works the same way, driven by a mysterious field called the inflaton, whose energy repelled gravity, causing spacetime to swell exponentially. The implications are staggering. Inflation explains why the universe appears flat like a sheet of paper stretched so large, its curves vanish from view. It accounts for the absence of exotic relics like magnetic monopoles, which would have been diluted to near non-existence during the expansion. And most mind-bending of all, it suggests our observable universe might be a vanishingly small bubble in an incomprehensibly vast multiverse, where other bubbles underwent their own inflation, each with different physical laws. Yet inflation isn't without its puzzles. Why did it start? Why did it stop? Some models propose collisions between these inflationary bubbles, leaving scars in the CMB we've yet to detect. Others suggest inflation is eternal, with new universes budding off endlessly like branches on a tree. Future experiments, like next-generation CMB observatories, aim to hunt for the faint gravitational waves inflation would have generated ripples in spacetime that could confirm this wild theory. From the subatomic to the cosmic, inflation binds the universe's story together. It's the reason we can look up at a smooth, structured night sky, and the reminder that the grandest chapters of existence might have been written in the blink of an eye. If you thought empty space was truly empty, think again. The vacuum of space is alive with invisible energy, crackling with particles that flicker in and out of existence like cosmic static. This is vacuum energy, a phenomenon so bizarre it challenges our very understanding of nothingness. At the quantum level, particles and antiparticles constantly pop into being, borrowing energy from the vacuum in fleeting pairs before annihilating each other in bursts of raw potential. These quantum fluctuations aren't just theoretical quirks. They generate real, measurable forces like the Casimir effect, where two uncharged metal plates placed nanometers apart in a vacuum inexplicably snap together. Why? Because the space outside the plates hosts more quantum fluctuations than the cramped space between them, creating a pressure differential that pushes the plates together with detectable force. It's as if the universe itself is pressing down on the void, proving that even in emptiness there's no escape from physics' grip. Dive deeper, and vacuum energy reveals even wilder implications. According to quantum field theory, these fluctuations represent zero-point energy, the baseline energy that remains even when a system is at absolute zero, its lowest possible energy state. Picture a spring that never stops vibrating, no matter how much you cool it. This energy isn't small either. Calculations suggest the vacuum's energy density should be astronomically high, enough to rip atoms apart instantly. Yet we don't see that chaos. Why? This discrepancy, known as the cosmological constant problem, is one of the biggest unsolved puzzles in physics. Einstein's equations treat vacuum energy as a repulsive force, that cosmological constant he later doubted, but its observed value is a staggering 120 orders of magnitude weaker than quantum theory predicts. Somewhere between math and reality, the universe is keeping a secret. The hunt for answers has led to mind-bending proposals. Could vacuum energy be harnessed like science fiction's warp drives or zero-point energy devices? Theoretically, yes, but practically, it's like trying to bottle lightning. The energy is everywhere, but accessing it requires manipulating space-time on scales we can't yet touch. Then there's vacuum decay, a chilling scenario where a bubble of true vacuum could form, rewriting the laws of physics at light speed and obliterating everything we know. It's unlikely, but the fact that it's even possible hints at how little we grasp the forces humming in the void. From shaping the fate of the cosmos to powering hypothetical future technologies, vacuum energy is the universe's quietest and most enigmatic powerhouse. It whispers that nothing is ever truly empty, and that the fabric of reality might be far stranger than we dare to imagine. Magnetic fields are the invisible architects of the cosmos, threading through planets, stars, and galaxies like cosmic puppet strings. While we often think of them as the reason compass needles point north, their true power spans scales from the atomic to the galactic. Take Earth's magnetosphere, a vast magnetic bubble shielding our planet from the sun's deadly solar winds. Without this force field, charged particles would strip away our atmosphere over millennia, leaving Earth as barren as Mars. But the magnetosphere isn't just a barrier, it's a dynamic sculptor. When solar storms collide with it, they trigger dazzling auroras, nature's own light show, as particles spiral along magnetic field lines, painting the sky with curtains of green and violet. Venture into the depths of space, and magnetic fields become even more formidable. In stellar nurseries, dense clouds where stars are born, these fields channel gas into swirling streams, controlling how fast material collapses into protostars. Too weak, and the cloud fragments chaotically, birthing a riot of small stars. Too strong, and star formation grinds to a halt, as if space itself hit pause. The iconic pillars of creation in the Eagle Nebula, their delicate fingers are shaped by magnetic pressures, resisting the destructive winds of nearby stars. Then there's the Milky Way's own magnetic skeleton, a web of fields stretching tens of thousands of light years. Though a million times weaker than a fridge magnet, this galactic scale force guides cosmic rays, energetic particles racing near light speed, bending their paths into spirals. Astronomers map these fields by studying starlight polarized as it passes through dust grains aligned by magnetism, revealing a hidden architecture woven into the galaxy's fabric. But perhaps the most dramatic displays come from neutron stars, where magnetic fields reach strengths that boggle the mind. Magnetars, a rare breed of neutron star, boast fields so intense they could tear apart atoms from 1,000 kilometers away. In 2004, a magnetar 50,000 light-years away unleashed a flare that temporarily compressed Earth's ionosphere, proof that magnetism isn't just a local phenomenon, but a universal language of power. From protecting life on Earth to orchestrating the birth of stars, magnetic fields are the silent conductors of the cosmic orchestra. They shape without touching, influence without visible trace, and remind us that some of the universe's most profound forces are the ones we can't even see. Plasma isn't just the fourth state of matter. It's the universe's dominant form, a roiling sea of charged particles that powers stars, shapes galaxies, and occasionally reminds us just how fragile our technology can be. Nowhere is this more evident than on our own sun, where plasma dances in a perpetual thermonuclear ballet, birthing phenomena like coronal mass ejections, solar storms so powerful they can unleash chaos on Earth with a single strike. Picture a tangled web of magnetic field lines suddenly snapping, flinging billions of tons of superheated plasma into space at speeds exceeding 1,000,000 miles per hour. That's a coronal mass ejection in action, and when one of these cosmic hurricanes collides with Earth's magnetosphere, the results range from dazzling auroras to satellite blackouts and power grid failures. Take the Carrington event of 1859, the most intense solar storm ever recorded. A coronal mass ejection slammed into Earth with such force that telegraph systems, the Victorian-era internet sparked and caught fire, while auroras lit up skies as far south as Cuba. Today, a storm of that magnitude could fry global communications, knock out GPS networks, and leave entire continents in the dark for weeks. In 2012, a Carrington-class ejection narrowly missed Earth, threading the needle between our planet and its orbit. Had it hit, experts estimate the damage could have cost over $2 trillion, but plasma's destructive potential is matched only by its creative power. Deep in the Sun's core, hydrogen nuclei plasma's building blocks slam together under crushing pressure, fusing into helium and releasing the sunlight that sustains life on Earth. This process, called nuclear fusion, is what keeps stars shining for billions of years. Scientists are racing to replicate it here on Earth, with projects like ITER and the National Ignition Facility aiming to harness star power in controlled reactors. The challenges are immense. Containing plasma hotter than the Sun's core requires magnetic fields strong enough to twist it into donut-shaped rings called tokamaks, where it can't touch and vaporize the reactor walls. Yet the payoff could be limitless clean energy, a prize worth the struggle. Then there's the Sun's more everyday fury, solar flares. These explosions on the solar surface unleash bursts of X-rays and radiation, ionizing Earth's upper atmosphere and disrupting radio signals. Airlines reroute polar flights during severe flares to avoid radiation exposure, while astronauts on the ISS take shelter in shielded compartments. Even satellites aren't safe. In 2022, a swarm of SpaceX Starlink satellites fell victim to a geomagnetic storm triggered by solar activity, burning up prematurely in the atmosphere. Yet for all its volatility, plasma is also a cosmic sculptor. The solar wind, a constant stream of charged particles, carves structures like comet tails and shapes planetary atmospheres. On Mars, where no global magnetic field exists to deflect these particles, the solar wind has stripped away most of what was once a thick atmosphere, leaving the planet a barren desert. Meanwhile, plasma filaments in galaxy clusters thread through the cosmos like invisible rivers, channeling energy across millions of light years. From powering stars to threatening civilization, plasma proves that the universe's most abundant substance is also its most dynamic. It's a reminder that the same forces that give us light can also bring darkness, and that understanding them isn't just science, it's survival. Tidal forces are the universe's silent shredders, invisible hands that stretch, squeeze, and heat celestial bodies with relentless precision. Nowhere is their power more dramatic than in Jupiter's gravitational grasp, where moons and comets endure cosmic tug-of-wars that reshape their very existence. Take comet Shoemaker-Levy 9, discovered in 1993. As it strayed too close to Jupiter, tidal forces stretched it like taffy, fracturing it into 21 fragments before the planet's gravity dragged them down in a fiery collision. The scars from those impacts lingered in Jupiter's atmosphere for months, dark bruises larger than Earth itself, proof of tides so strong they turned a comet into celestial confetti. But Jupiter's tidal grip doesn't just destroy, it also transforms. Look at Io, the solar system's most volcanic world. Squeezed between Jupiter's gravity and the competing pull of neighboring moons, Io's interior is kneaded like dough, generating so much friction that its crust crackles with hundreds of active volcanoes. Sulfur-spewing vents paint its surface in neon yellows and fiery oranges, while lava lakes simmer at temperatures hotter than Earth's mantle. This isn't just geological activity, it's tidal heating in action, a process so intense it keeps a moon the size of ours molten at its core. The mechanics are deceptively simple. Just as Earth's tides bulge toward the moon, Jupiter's gravity stretches its moons unevenly. But unlike Earth's gentle oceanic rhythms, Jupiter's tides are relentless. Io's orbit is elliptical, meaning its distance from Jupiter varies, and with each pass, the planet's gravity yanks harder on the near side than the far side. This constant flexing generates internal heat, fueling eruptions that blast plumes 300 miles into space. Europa, another Jovian moon, experiences similar forces, but instead of fire, its tidal energy maintains a global subsurface ocean locked beneath an icy shell. Tidal forces aren't unique to Jupiter. Saturn's moon Enceladus sprays geysers of water into space, thanks to tidal flexing from its ringed parent. Even distant binary star systems and black holes exhibit tidal extremes, spaghettifying anything that ventures too close. Yet Jupiter's system remains the ultimate classroom for studying these phenomena. From comet disintegration to moon-scale pressure cookers, it's a showcase of how gravity's subtle tugs can rewrite the rules of planetary science and hint at where life might hide in the frozen depths of tidal heated oceans. Quantum entanglement is the universe's ultimate magic trick, a phenomenon so baffling even Einstein called it spooky action at a distance. Here's the puzzle: two particles become linked, their fates intertwined no matter how far apart they drift. Change one and the other instantly responds, as if telepathy were encoded into the fabric of reality itself. This isn't hypothetical, it's been proven in labs across the globe, defying our classical intuition about how the world should work. Take the famous EPR paradox named after Einstein, Podolsky, and Rosen. In 1935, they argued that quantum mechanics couldn't be complete because it allowed for this eerie connection, what Einstein dismissed as spooky. Their thought experiment imagined two entangled particles flying apart. Measure one spin here, and the other's spin would snap into the opposite state instantly, even if it were light years away. To Einstein, this implied hidden variables, secret instructions guiding the particles' behavior. But decades later, physicist John Bell proved otherwise. His theorem showed that no local hidden variables could explain the results seen in experiments. When scientists finally tested it using entangled photons separated by kilometers, the particles matched their partner's state faster than light could have carried any signal between them. The verdict: the universe doesn't play by classical rules. Modern experiments have only deepened the mystery. In 2017, Chinese scientists sent entangled photons from a satellite named Mishus to ground stations over 700 miles apart. No matter the distance, the particles remained perfectly correlated. Then there's quantum teleportation, not the sci-fi kind, but the transfer of quantum states between particles using entanglement. Researchers have pulled this off across cities and even between Earth and space, proving that information can be beamed without physical travel. So, what's really happening? One interpretation is that entangled particles aren't separate entities at all but part of a single quantum system, no matter how far apart they appear. Another wild idea is that the universe is fundamentally non-local, that space is just an illusion and everything is connected in ways we can't yet see. For now, entanglement remains both a tool and a riddle, powering cutting-edge tech like quantum cryptography while challenging us to rethink the nature of reality itself. Perhaps the most astonishing part: we're just beginning to harness it. Quantum computers use entanglement to perform calculations at speeds impossible for classical machines, while ultra-secure quantum networks could one day make hacking obsolete. Yet for all its promise, entanglement whispers something profound: that beneath the surface of our orderly universe lies a web of invisible connections waiting to be unraveled. Black holes aren't the cosmic vacuum cleaners we once thought. They leak. Slowly, faintly, but inevitably they evaporate, thanks to a phenomenon called Hawking radiation. Picture this: space isn't empty, not even close. At the quantum level, it's a seething ocean of virtual particles, pairs of matter and antimatter that blink in and out of existence so fast they usually cancel each other out. But near a black hole's event horizon, something extraordinary happens. If one of these particle pairs appears right at the edge, gravity's immense pull can yank one particle into the abyss while the other escapes, stealing a tiny bit of the black hole's energy in the process. Over trillions of years, this slow trickle of lost energy causes the black hole to shrink, eventually vanishing in a final, faint pop of radiation. To grasp how bizarre this is, imagine a magician's hat that spontaneously produces rabbits, but every time a rabbit jumps out, the hat loses a little weight. The rabbits in this case, the escaping particles, aren't coming from nowhere. They're being paid for by the hat's own mass. Now scale that up to a cosmic level, and you've got Hawking radiation, a process so counterintuitive, even Stephen Hawking himself initially doubted it. The math checks out, though. In 1974, Hawking calculated that black holes aren't just gravitational traps. They're quantum objects with temperature, emitting thermal radiation like a stove burner glowing red hot. The smaller the black hole, the hotter it burns, shrinking faster as it nears its end. Here's where it gets even weirder. This radiation isn't coming from inside the black hole. It's generated just outside the event horizon, meaning the information swallowed by the black hole isn't being returned, at least not in any recognizable form. This creates the infamous black hole information paradox, a puzzle that's kept physicists awake for decades. If information can't be destroyed, where does it go when the black hole evaporates? Some theories suggest it's scrambled into the radiation, encoded in ways we can't yet decipher. Others propose wild ideas like holographic universes, where all the data is stored on the black hole's surface like a cosmic hard drive. Yet Hawking radiation isn't just theoretical musing, it has real cosmic consequences. Primordial black holes, hypothetical tiny black holes formed in the early universe, could be evaporating right now, their death throes lighting up as gamma-ray bursts. And in the far, far future, long after stars have burned out, Hawking radiation will be the last flicker of activity in an otherwise dark and silent cosmos, the final whisper of black holes dissolving into nothingness. It's a humbling thought. Even the mightiest monsters in the universe have an expiration date, their reign undone by the tiniest flickers of quantum uncertainty. So next time you gaze at the night sky, remember somewhere out there, black holes aren't just consuming light, they're leaking it one particle at a time in a slow cosmic dance between gravity and quantum weirdness. And in that paradox lies one of the deepest mysteries of all. How the universe balances its most destructive forces with the delicate rules of quantum mechanics, ensuring nothing, not even a black hole, lasts forever. Cosmic strings are among the most exotic relics of the early universe, theoretical cracks in spacetime itself, forged in the fiery chaos of the Big Bang. Picture the universe a fraction of a second after its birth, undergoing rapid expansion and phase transitions. As it cooled, flaws might have formed in the fabric of spacetime, like cracks in ice as it freezes. These one-dimensional defects, thinner than an atom but stretching across cosmic distances, would carry unimaginable density. Just a single inch of cosmic string could weigh as much as Mount Everest. The idea isn't just wild speculation. It emerges from well-established theories of particle physics and cosmology, suggesting that these structures could be lurking undetected, warping space around them like invisible guitar strings tuned to the key of gravity. What makes cosmic strings truly bizarre is how they distort reality. Imagine one slicing through the solar system. Unlike black holes or planets, a cosmic string wouldn't pull objects toward it with gravity. Instead, it would create a peculiar gravitational lensing effect. Double images of stars or galaxies appearing on either side of the string, as if spacetime itself were split by an unseen razor. This kink in the universe would mean that if you flew a spaceship around a cosmic string in a perfect loop, you could return to your starting point before you even left, thanks to the warp topology. Time travel, not quite, but close enough to bend the mind. The hunt for cosmic strings has turned up empty so far, but astronomers have a few tricks to spot them. One method involves searching for abrupt jumps in the cosmic microwave background, the afterglow of the Big Bang where a string's gravitational tug might have left faint scars. Another relies on gravitational waves. If two strings crossed and snapped like rubber bands, they'd send ripples through spacetime detectable by observatories like LIGO. Even pulsars, the universe's precision clocks, could reveal strings. Their regular radio pulses would waver if a string passed between them and Earth, warping the path of their signals. Yet cosmic strings aren't just celestial oddities. They might hold the keys to cosmic structure. Some theories suggest these defects could have acted as gravitational scaffolding in the early universe, seeding the formation of galaxies by creating dense regions where matter clustered. Others propose that they're the source of ultra-high-energy cosmic rays particles that strike Earth's atmosphere with energy surpassing anything our largest particle colliders can produce. And if they exist, they'd be near indestructible, surviving from the universe's first moments to the present day, vibrating like cosmic violin strings and humming gravitational waves into the void. The most thrilling possibility, cosmic strings could be time capsules. If discovered, they'd offer a direct glimpse into the universe's infancy, revealing conditions we can't replicate in any lab. They're a reminder that the cosmos might be threaded with invisible fractures, flaws in the grand design that, instead of weakening the universe, add to its mystifying complexity. Until we find one, they remain ghostly threads woven into the tapestry of theory, waiting to be pulled. Wormholes sound like pure science fiction tunnels through space-time, connecting distant corners of the universe in the blink of an eye. But what if these cosmic shortcuts weren't just Hollywood fantasy? Enter Einstein-Rosen bridges, the theoretical underpinnings of wormholes born straight from the equations of general relativity. In 1935, Albert Einstein and Nathan Rosen explored the math behind black holes and stumbled onto something astonishing. Their solutions hinted at bridges linking 2 points in spacetime, like a cosmic subway system hidden within the fabric of reality. Interstellar's portrayal of Gargantua gave us a visually stunning glimpse of this idea. Remember the scene where Cooper plunges into the black hole, only to emerge in a tesseract of folded time. While the movie took creative liberties, the core concept wasn't dreamed up in a writer's room. The equations suggest that if you could stabilize a wormhole's throat, preventing it from collapsing the instant it forms, you might traverse vast distances without breaking light speed. Picture stepping into a portal near Earth and emerging near Alpha Centauri, 4.37 light-years away in mere seconds. But here's the catch: wormholes, as we understand them, are catastrophically unstable. The moment one forms, the intense gravitational forces at its throat would snap it shut like a rubber band, crushing anything inside. To keep it open, you'd need exotic matter, a hypothetical substance with negative energy density that could repel gravity's crushing grip. Think of it as cosmic duct tape propping the tunnel walls apart against nature's inclination to collapse them. The problem: exotic matter defies known physics. While quantum mechanics allows for fleeting negative energy states like in the Casimir effect, assembling enough to stabilize a wormhole remains firmly in the realm of speculation. Yet the math persists, fueling wild but tantalizing possibilities. Some theories suggest wormholes could be time machines. Enter one mouth at the right velocity, and you might exit before you even left. Others propose they're fingerprints of a quantum foam, popping in and out of existence at the smallest scales of spacetime. And if cosmic strings exist, their immense tension might theoretically warp spacetime into traversable pathways, though the energy required would dwarf anything humanity could harness. For now, wormholes remain a breathtaking what if, a reminder that the universe's rulebook might still have chapters we've yet to read. They challenge us to imagine not just how space bends, but how it might fold, offering shortcuts to the farthest reaches of the cosmos, if only we could survive the trip. If black holes are the universe's ultimate drains, swallowing everything that crosses their path, white holes are their hypothetical opposites: cosmic fire hydrants blasting matter and energy outward with relentless force. Think of them as black holes running in reverse, where nothing can enter, but anything inside is violently expelled. The math allows for this bizarre possibility. While black holes trap light behind an event horizon, white holes would have an event horizon that only lets things out, like a one-way exit door welded shut from the outside. The idea first emerged from the same equations that predicted black holes. When physicists like Roy Kerr and Roger Penrose mapped the geometry of spacetime around these objects, they found solutions that didn't just describe collapse, they hinted at explosions. Penrose diagrams, those twisted maps of spacetime, show black holes and white holes as mirror images, connected by a theoretical bridge called an Einstein-Rosen wormhole. But while black holes are everywhere, lurking in galaxy centers, hiding in binary systems, white holes remain purely hypothetical. No one's ever seen one, and there's a good reason for that. Unlike black holes, which form naturally from collapsing stars, white holes would require wildly exotic conditions to exist. They'd either need to be born in the Big Bang itself, spewing out primordial energy like a cosmic pressure valve, or emerge from a black hole's death throes via Hawking radiation. Some theories even suggest that when a black hole evaporates completely, it might rebound as a white hole, recycling its consumed material back into the universe in a final burst. The most tantalizing link: white holes could explain fast radio bursts, those mysterious millisecond-long blasts of energy from deep space. While most FRBs are traced to neutron star collisions or magnetars, a handful defy explanation, appearing as isolated, ultra-powerful flashes. Could these be white holes coughing up fragments of a long-vanished universe? It's a stretch, but the math doesn't rule it out. Yet the real magic of white holes lies in their theoretical implications. If they exist, they'd challenge our understanding of causality, rewriting the rules of what can or must happen in spacetime. They're a reminder that the universe's strangest forces might not just be hidden in darkness, but waiting in the unexplored corners of a physicist's chalkboard, where even the wildest ideas refuse to be erased. Among all the titanic forces shaping the universe, one of the most haunting remains the silence. We live in a cosmos teeming with hundreds of billions of galaxies, each containing countless stars and planets, yet we've found no definitive sign of other civilizations. This eerie quiet is the Fermi Paradox, the stark contradiction between the high probability of alien life and our total lack of evidence for it. Named after physicist Enrico Fermi's famous lunchtime question, "Where is everybody?" This paradox forces us to confront unsettling possibilities about the fate of intelligent life in the universe. The numbers alone make the silence bewildering. With over 200 billion stars in our Milky Way and most hosting planets, even conservative estimates suggest thousands of advanced civilizations should exist. Some may have arisen billions of years before us, granting ample time to colonize the galaxy, yet Earth remains untouched and our radio telescopes hear only static. One compelling explanation is the Great Filter theory, which proposes that some catastrophic barrier prevents life from reaching interstellar stages. The terrifying question isn't just where the filter lies, but whether it's behind us or ahead. If the filter is in our past, like the improbable jump from single-celled to complex life, we might be rare survivors. If it's ahead, a looming existential threat like nuclear war or runaway AI, then the universe might be littered with civilizations that annihilated themselves before they could spread. Then there's the energy question. Given enough time, an advanced civilization should harness stellar-scale power, perhaps by constructing Dyson spheres, hypothetical megastructures that encase stars to capture their energy. These would glow with waste heat detectable across galaxies, yet our infrared surveys find no clear signs. Some argue that super-advanced beings might use technologies beyond our comprehension, rendering their presence invisible. Others suggest they've transcended physical forms, uploading consciousness into virtual realms, effectively vanishing from the observable universe. Could it be we're simply too early? The universe is 13.8 billion years old, but Earth didn't form until 9 billion years in. Future civilizations might arise long after we're gone. Or perhaps space is simply too vast, the distances between stars an impassable moat. Every hypothesis carries its own existential weight, reminding us that the silence isn't just a puzzle, it's a mirror reflecting our own fragility. The Fermi Paradox forces us to grapple with profound uncertainties. Are we alone? Are we doomed? Or is the universe hiding civilizations in ways we've yet to imagine? The answer could rewrite not just our place in the cosmos, but our future. And until we know, the stars will keep their secrets, leaving us to wonder if the greatest force of all is the one keeping us apart. Entropy isn't just a scientific concept, it's the silent force pushing the universe toward ultimate chaos, one irreversible moment at a time. Picture an ice cube melting in a glass of water. The orderly structure of ice crystals breaks down into disordered liquid, and no matter how long you wait, those water molecules will never spontaneously rearrange themselves back into a perfect cube. That's the second law of thermodynamics in action. In any closed system, entropy, a measure of disorder, always increases. It's why time has a direction, why heat flows from hot to cold, and why the universe is marching inevitably toward what scientists call heat death, a state where all energy is evenly distributed, no work can be done, and everything grinds to a silent, frozen halt. The implications are staggering. Every time you scramble an egg, burn fuel in your car, or even exhale warm breath into cold air, you're adding to the universe's tally of irreversible change. Stars shining, that's entropy increasing as nuclear fuel burns. Galaxies colliding, entropy again, transforming ordered motion into chaotic heat. Even life itself is a temporary rebellion against this trend, creating pockets of order while accelerating entropy elsewhere. Your body maintains structure by constantly breaking down food, a process that releases far more disorder than the neat arrangement of your cells represents. Cosmologically, this leads to a chilling finale. As stars exhaust their fuel and black holes evaporate via Hawking radiation, the universe will cool to near absolute zero over trillions of years. Matter itself may decay into radiation, spreading thinly across an ever-expanding void. No more temperature differences, no more gradients to drive change, just a vast, featureless equilibrium. Some theories suggest quantum fluctuations might spark new universes from this entropy graveyard, but for our cosmos, the arrow of time points only toward stillness. Yet entropy isn't just doom and gloom. It's what makes the universe creative. Without it, nothing would ever change. Snowflakes wouldn't form, storms wouldn't rage, and life couldn't evolve. It's the reason time feels like it flows forward, giving us history instead of endless repetition. The very fact you can remember yesterday but not tomorrow is tied to entropy's relentless rise. In a strange way, this force of disorder is what makes existence meaningful, sculpting the transient beauty of galaxies, civilizations, and conscious minds from the cold equations of thermodynamics. The universe isn't just running down, it's unfolding, one irreversible moment at a time. The multiverse isn't just science fiction, it might be science fact, hidden in the fine print of cosmic inflation and string theory. Imagine our universe as one bubble floating in an endless cosmic froth, where every bubble houses its own unique laws of physics, its own version of reality. This isn't just wild speculation. It's a natural consequence of inflationary theory, which suggests that when spacetime expanded faster than light during the Big Bang, pockets of space could have pinched off into separate universes, each with its own destiny. Some might have stars and galaxies like ours, while others could be empty voids or filled with exotic particles we can't even name. String theory takes this idea even further. Picture the cosmos as a vast ocean where our universe is just one ripple on the surface of a higher dimensional brane, short for membrane. These branes could float in an unseen dimension, occasionally colliding like sheets of paper drifting in the wind. When they do, the energy released might spark new big bangs, birthing entire universes in cosmic fireworks. Animations of these collisions show spacetime itself warping, sending shockwaves that could reset the laws of physics in the newborn cosmos. It's a dizzying thought. Every time brains clash, a new universe might ignite, each with its own constants, its own quirks of nature. But how could we ever prove such a thing? One clue lies in the cosmic microwave background, the afterglow of the Big Bang. If our universe had ever brushed against another, the collision might have left a faint imprint like a bruise on the sky. Astronomers have searched for these anomalies, though none have been confirmed yet. Another hint could come from gravitational waves. Certain models predict that brain collisions would send ripples through spacetime at frequencies we might one day detect. The implications are staggering. In a multiverse, every possible outcome might exist somewhere: worlds where dinosaurs never went extinct, where humanity never evolved, or where the laws of physics make life impossible. Some universes might be stillborn, collapsing moments after birth, while others could harbor civilizations far older and wiser than ours. It's humbling to think that our entire cosmos might be just one page in an infinite library of realities, each written in a different physical language. Yet the multiverse isn't just a philosophical curiosity, it's a potential solution to one of physics' deepest puzzles: why our universe seems so finely tuned for life. If countless universes exist with random physical constants, it's no surprise we find ourselves in one where conditions are just right. The alternative, that our universe is the only one perfectly calibrated by chance, seems almost too improbable to believe. Whether through colliding brains or inflationary bubbles, the multiverse challenges us to rethink not just where we are, but what reality even means. It suggests that the cosmos might be vaster and stranger than we ever dreamed, a cosmic kaleidoscope where every twist reveals a new universe, a new set of rules, and perhaps a new version of ourselves. From the crushing grip of black holes to the universe-stretching push of dark energy, we've journeyed through forces that dwarf human imagination in both scale and power. If there's one humbling truth these phenomena reveal, it's how small we truly are in the cosmic scheme, mere specks on a pale blue dot, orbiting an unremarkable star in one galaxy among trillions. Yet here we are, tiny but curious, unraveling the universe's greatest mysteries one equation at a time. Before we close, let's revisit 5 forces that redefine awe. First, gravity, the silent sculptor bending spacetime into the cosmic web we call home. Second, dark energy, that enigmatic pressure accelerating the universe's expansion, hinting at futures we can scarcely comprehend. Third, the strong nuclear force, nature's ultimate glue, binding atomic nuclei against electromagnetic rebellion. Fourth, black holes, the spacetime maestros twisting reality into knots where even light surrenders. And fifth, quantum entanglement, proving the universe connects particles across vast distances in ways that still baffle our intuition. Each of these forces whispers a profound truth. The universe operates on rules far stranger than fiction, where the fabric of reality itself is pliable, brutal, and breathtakingly beautiful. So the next time you gaze at the night sky, remember, you're not just looking at stars, you're witnessing the aftermath of cosmic collisions, the glow of nuclear furnaces, and the fingerprints of forces that shaped everything from atoms to galaxies. Which of these cosmic titans left you most awestruck? Was it the star-crushing might of neutron stars or the ghostly influence of dark matter? Drop your thoughts in the comments, and if there's a cosmic mystery you'd love us to explore next, shout it out. The universe is vast, the questions endless, and our journey to understand them has only just begun. Until next time, keep looking up, because the cosmos isn't just out there. It's in every atom of your being and every question you dare to ask.